So in ELE 110, we been studying the half-wave rectifier, the center tap full wave, and as well as the bridge rectifier. As mentioned prior to us going on spring break here, what we wanted to do is take our final test in this section and get this done with. So what we're going to do is we're waiting off until March 30th. This will go active. The test will go active on March 30th, and I'll have a week to complete the test. So the first circuit I have up here is a half-wave rectifier. This is called a half-wave rectifier. And we know this because what we'll have here is a waveform. So if we look at this waveform, so this is the upper peak, and that's the lower peak right down there. So we know that this diode right here will go forward bias this thing, but it won't forward bias the lower peak because of the biasing of the transistor. So in this case, let's look at all the parts of it. First of all, we have 120 volts, 60 hertz. And if we want to know the secondary voltage, we can actually use this equation. NP/NS is equal to VP/VS. This is just a ratio equation. So if we actually look at this and we do it, this is a 6-to-1 ratio here. So this is the number of turns in the primary to the number of turns in the secondary. 6-to-1 is equal to, well, we know the primary voltage is 120 volts to voltage in the secondary. So we can look at that. So let me get this thing zoomed in a little bit more here for you. There we go. So if we actually do the math here, we have 120 divided into 6 gives us 20 volts. So 20 volts secondary. Now, one thing on the test will be what type of transformer. This is called an iron core transformer because I have two lines through the middle that designates as an iron core. And this says 20 volts RMS. There we go, RMS. That means we have 20 volts RMS here, a sinusoidal waveform. So what this will look like on our circuit will be this. So this is our input. So we know that the input actually looks like something like that. And then our output is going to be an output at A. Let's call this at A. And A is going to represent this. So basically what we're going to have is really a large amount of area that's going to be open because the lower peak right here is being not forward biased. It's not going to be there. So basically what we're going to have is that, just like that. So we can do some math here to figure out some of this stuff. So we can find voltage peak. This is 20 volts RMS times it by 1.414. So we get 20 times it by 1.414 gives me 28.28 volts peak. Now, if I want to find volt peak at the diode, after the diode, which is basically what we're going to do is take the 28.28 volts peak and minus it by 0.7 volts. And 0.7 volts is our silicon diode, so we come up with 27.58. 27.58 volts peak diode. Now, we can also now solve for the voltage at the voltage DC. We call this the average DC. So we take 0.318 times it by voltage peak of the diode, and we get 8.77 volts, 8.77 volts. Now, this voltage is just this voltage up here. So right now what we have coming across is this, and this is voltage, what we call voltage VDC. So what we actually have done, let me put that back down a little bit there, about there, is VDC. So VDC, gives us an approximation. This is with ripple. This is with ripple. So if we want to know what happens when we want to get rid of this ripple, so how do we get rid of the ripple? Well, we'll have to put a capacitor in. A lot of times we'll put in a capacitor that's pretty large, and we call this C1. So let's set C1 is equal to 2,500 microfarads. Well, it's 2,500 microfarads. We can easily start finding the voltage ripple. So we can find the voltage ripple, that's VR. is going to be equal to voltage peak of the diode times 1 minus exponential of our negative T over RC. And RC is our time constant. Negative T, so let's look at negative T. Remember, T for this is going to be 60 hertz because we have one diode and this is a half-wave rectifier. So we can say up here, let's put this back up here for a second. T is equal to 60 hertz, or whoops, not T. That's frequency is equal to 60 hertz. T is equal to 1 divided into 60, gives us 16.66 milliseconds. So we can use that down here in this equation. So again, frequency is 60 hertz, time is 1 over the frequency, so it comes out to 16.66 milliseconds. So let's figure this out. So the voltage ripple is going to be equal to voltage peak, which was 27.5 volts peak, times it by 1 minus exponential, get this really big for you guys, negative 16.67 milliseconds over the RC. R is 100 ohms, and the C is 2,500 microfarads. So now we can easily find the ripple. I'm going to make that big. So our ripple is going to be equal to, so our ripple, if we put it into this equation, is going to be about 1.77 volts ripple. So let's take a look at that ripple. Let's find out what that ripple is all about. So if we look at this, in a larger view. So if we look at this, this is without the capacitor. Let me do that again. Let me run that again. That's a mistake. So remember, half wave, not full wave, half wave. So, so if we look at this half wave, so we know that the VDC, which is about right here, that's VDC without the capacitor. So with the capacitor, what's going to happen is that, let's superimpose this thing onto the circuit here. So if we superimpose this on here, and I'm just going to draw the bottom one so it's lining up a little better here. So we know that right at this point, this is going to be the upper, and then the lower is going to disappear, and we're going to keep going. Just like that. We're just going to keep on going. But what's going to happen with the capacitor, so this is your input, and this is with cap. So what's going to happen, not with the cap right here, but this is what's going to happen. What's going to happen is you're going to have a charge and a discharge. This is with the cap, this triangular wave. And all of a sudden this thing's going to come down all the way. And let's see, it's going to do that, it's going to do that, it's going to do this. So it's going to give us almost like a sawtooth waveform on that. What's going to give us is going to be a sawtooth waveform. So what we're going to get is a sawtooth waveform, just like that. And this is called the ripple. This is called the V ripple right here. And we calculated that to be 1.77 volts. So we can say that a half-wave rectifier is really cheap, not accurate. It's not accurate, but it works. It does what it needs to be done. So if you have any questions about the half wave, please. So a full wave bridge rectifier uses 4 diodes to achieve what we call full wave rectification. What's nice about this one is, unlike the center tap, is that we get the full RMS voltage across the transformer. We don't have to split it. So in this case, these diodes, two of these diodes are going to conduct at a single time. So on the upper peak, we call the upper peak here. So if we trace it through, this one's going to conduct, then it's going to come back this way, and it's going to come back, conduct through this, and then back out. Now, likewise, on the reverse end of it, on the lower end of the peak, what we're going to have is it's going to come through, let's see, it's going to come through this way, come through here, come back through here, and it's going to come back through that way. So basically, it's coming through here, back through here, down, across, and then out back here. So that's how we're getting that one. And this upper peak is coming this way, comes back this way, comes back, makes a nice circle, and it goes over there. So we still have voltage secondary RMS is 20 volts, which is fine. Now voltage secondary at peak is going to be 28.28. Same thing, but look what's different here. Voltage secondary with the diode now included is 28.28 minus 1.4 is 26.88. 26. Couple things to pay attention to on here. Since we are now using both the lower and upper peaks here, our frequency is going to be 2 times 60, which is 120 hertz, so our time is now 8.33. This needs to be included in our ripple equation. So before we get to the ripple, let's look at VDC. VDC is 0.636 times 26.88, which gives us 17.09. So we get about 17.09, which is about right about there. This is 17.09 volts DC. So let's take a look at the final part of this. That's V ripple. V ripple is going to be equal to V peak with diode. I'm going to call it VPD, times that by 1 minus E exponential negative T divided into RC. So, well, I'm going to have to include a capacitor into this equation here. So let's say we do. Let's say we include a capacitor, a nice big capacitor. It's called 3,000 microfarads. Remember, these are electrolytics, so they have polarity, positive and negative. So if we do that, we get, so what we're going to get here, if we put in all our numbers, we're going to get is a ripple of 0.736 volts ripple. So if we look at that on a screen, what's going to look like is actually it's going to look like it's going to be really small. It's going to be really small. So these are the charge and discharge of the capacitor. Whoops, the charge and discharge of the capacitor right there. What we actually want to have is a straight line. We want a full straight line. That's what we want. No ripple, no nothing. To achieve that, we increase the value of the capacitor. That'll be on the test. So this is a full wave bridge rectifier. Some of the simple equations I've used. We also have a center tap transformer. Now, center tap transformer taps off the center point right here. And that means that this 20 volts, that means there's 10 up here and 10. So we'd have to use 10 instead of the 20. That's why the bridge rectifier is more expensive. It's pretty much better in all aspects of it, but it's expensive. It can be very expensive. This diode array can be expensive when it comes to purchasing. These things can be 4, 5, 10, 20 amps, whatever you need to be. The other issue with this is that that if you don't pay attention to the polarity on here, you can actually cause the capacitor to actually explode. So if you have any questions about full wave, bridge, half wave rectifiers, or even center tap transformer, just email me. Thank you.